For 13 years, NASA's Cassini spacecraft orbited Saturn, capturing breathtaking images and making groundbreaking discoveries. But as the spacecraft made its final dive toward certain destruction, something unexpected happened. The data it sent back revealed that scientists didn't understand Saturn at all, and the closer Cassini looked, the more questions emerged that could rewrite everything we thought we knew about our solar system. On September 15, 2017, one of the most ambitious missions in the history of space exploration came to an end. But this wasn't just any ending. This was a carefully orchestrated finale, a dramatic conclusion to a story that began 2 decades earlier when a spacecraft left Earth on a 7-year journey to reach the ringed planet. The Cassini-Huygens mission was a collaborative effort between NASA, the European Space Agency, and the Italian Space Agency. It represented the combined knowledge and expertise of thousands of scientists, engineers, and dreamers who believed that we could study Saturn up close and learn secrets about our solar system that had eluded us for centuries. When Cassini arrived at Saturn in 2004, the scientific community had expectations, they had theories, they had models built on centuries of observation and decades of computational analysis. Astronomers thought they understood what Saturn was. They believed they knew how its atmosphere worked, how its rings formed, and what lurked beneath those swirling clouds of hydrogen and helium. But what they didn't anticipate was that spending 13 years in intimate contact with this gas giant would fundamentally challenge nearly everything they thought they knew. Saturn had been studied from a distance for so long that scientists had developed a false confidence in their understanding. The models had been tested, refined, and improved countless times. They seemed robust and well-established. Yet the universe has a way of humbling human knowledge, of revealing that our greatest theories are merely approximations of a reality far more complex and surprising than we had imagined. The journey itself was remarkable and complex. Cassini wasn't designed to reach Saturn in the most direct path possible. Instead, the spacecraft had to use gravitational assists from other planets to gain the necessary velocity while minimizing fuel consumption. It swung past Venus twice, flew by Earth once, and encountered Jupiter before finally arriving at Saturn. Each maneuver was precisely calculated, each trajectory planned years in advance by teams of orbital mechanics specialists. Scientists had one shot to get this right. There were no second chances, no do-overs in space exploration. Once Cassini launched from Earth in October 1997, the mission was committed. For 7 long years, the spacecraft traveled through the darkness of space, covering billions of kilometers through the vacuum. And when it finally reached its destination, it would remain there for more than a decade, studying the most visually spectacular planet in our solar system with tireless dedication to science. When Cassini arrived at Saturn, it wasn't alone. Piggybacked aboard the orbiter was a smaller lander called Huygens, built by the European Space Agency. Huygens had one mission: to land on Saturn's largest moon, Titan. In January 2005, just months after arriving at Saturn, Huygens detached from Cassini and parachuted through Titan's thick atmosphere, eventually landing on its frozen surface. The images it sent back were revelatory. Titan wasn't just another dead moon. It was a world with weather, with clouds, with rain and oceans. But instead of water, Titan's oceans were made of liquid methane and ethane. Here was a world that scientists now believe could potentially harbor exotic forms of life, a place where life as we understand it might exist in forms we've never imagined. But Huygens was just one part of Cassini's story. While the lander explored Titan's surface, Cassini remained in orbit, studying the Saturnian system from above. Over the next 13 years, Cassini would make discovery after discovery. The spacecraft had a suite of sophisticated instruments designed to observe, measure, and analyze every aspect of Saturn and its moons. Its cameras captured images of stunning clarity. Its spectrometers analyzed the composition of Saturn's atmosphere and rings. Its magnetometer measured the planet's magnetic field. Its gravity instruments tracked the precise position of the spacecraft to detect the gravitational pull of Saturn and its rings. One of Cassini's most significant discoveries came early in its mission. Scientists found that Saturn's moon, Enceladus, a small moon covered in ice, was shooting geysers of water into space from its south pole. This was unexpected. Enceladus looked frozen, dormant, yet here it was ejecting plumes of material into space. The plumes were spectacular, towering thousands of kilometers into space before raining back down onto the moon's surface and into Saturn's magnetosphere. Cassini's instruments tracked these plumes, analyzed their composition, and provided stunning images of this geothermal activity. Further analysis revealed something even more remarkable. Beneath Enceladus's icy crust lay a global ocean of liquid water, vast and deep, containing more water than all of Earth's oceans combined. Moreover, the geothermal activity detected in these plumes suggested something that had profound implications for the search for life beyond Earth. Enceladus had hydrothermal activity occurring in its ocean, just like on Earth. On Earth, Eons teem with exotic life forms that derive energy not from the sun, but from chemical reactions around those vents. These extremophils thrive in conditions that would be lethal to most other organisms, proving that life can exist in places far removed from sunlight and the chemistry we normally associate with biological systems. Enceladus suddenly became one of the most promising places in our entire solar system to search for life. Future missions to Enceladus are already being planned, with scientists eager to send probes that could drill through the ice and sample the ocean below, searching for signs of microbial life that might exist in those dark, warm waters. Saturn's rings also captured Cassini's attention and revealed mysteries of their own. The rings had long fascinated astronomers, stretching back centuries to when Galileo first glimpsed them through his telescope and wondered what they were. When Cassini arrived at Saturn, the rings had been studied by many spacecraft, but no mission had examined them in such intimate detail. Cassini found that the rings were far more complex than anyone had imagined. They were composed of countless particles, ranging in size from tiny grains to blocks as large as houses, all orbiting Saturn in precise gravity-defined patterns. Within the rings, Cassini discovered intricate structures never before observed. There were wave patterns created by gravitational interactions with moons, subtle undulations in the ring material that traced out the orbital resonances of distant moons. The spacecraft also identified propellers, small features created by moonlets embedded within the rings as they attempted unsuccessfully to open gaps in the ring material. These tiny moons, some only a few kilometers across, pushed on the surrounding ring particles, creating distinctive V-shaped patterns that could be identified in high-resolution images. The origin of Saturn's rings remained a mystery, though Cassini's observations provided tantalizing clues about how they might have formed. Some scientists believe the rings were debris from a moon that had been destroyed, either early in Saturn's history, when giant impacts were common, or more recently through a cosmic collision between two moons. Others propose that the rings formed from leftover material that never coalesced into a moon. The rings, scientists realized, might not be permanent features. Over millions of years, Saturn's gravity and the solar wind could cause the rings to gradually spiral inward and disappear. This meant that Saturn's current rings might be relatively young in cosmic terms, perhaps only hundreds of millions of years old, rather than dating back to the formation of the solar system itself. For over a decade, Cassini dutifully orbited Saturn, sending back images and data that captivated the public imagination and advanced scientific understanding. The spacecraft became a window into a distant world, showing us wonders we could only read about in textbooks. But nothing lasts forever, and Cassini was no exception. The spacecraft had been designed for a mission lasting around 4 years. NASA had granted 2 mission extensions, keeping Cassini operational far longer than originally planned. By 2017, the spacecraft was running low on fuel. The engineers knew the end was approaching, but before Cassini would plunge into Saturn's atmosphere and be destroyed, they decided to make one final audacious push to gather the most valuable data possible. This final phase was called the grand finale. NASA's planners designed a series of unprecedented orbits that would take Cassini through a region no spacecraft had ever explored. Between Saturn and its rings exists a narrow gap, roughly 2,000 kilometers wide. This gap had never been traversed by any spacecraft before. It was considered too risky earlier in the mission. Flying through this region posed dangers. Particles from Saturn's rings and atmosphere could damage the spacecraft. But now, with the mission coming to an end anyway, it seemed worth the risk. The scientific potential was extraordinary. Beginning in April 2017, Cassini began its grand finale. Over the next 5 months, the spacecraft completed 22 breathtaking dives through the gap between Saturn and its rings. Each dive took the spacecraft closer to Saturn than ever before, plunging down into regions where no human-built machine had ventured. The gap between Saturn and its rings is a treacherous region. Scientists had worried that Cassini might be damaged by particles from the rings or buffeted by the intense gravitational and magnetic fields close to Saturn. But the mission planners had calculated the risks carefully. They had determined that in the final months of the mission, when fuel was running out anyway, the risk was worth taking. The spacecraft oriented its large dish-shaped antenna forward as a shield against ring particles, using its own body as protection for the more delicate instruments behind it. During these grand finale dives, Cassini's instruments recorded measurements with unprecedented precision. The gravity field of Saturn was measured to an accuracy never before achieved, providing data that was accurate to levels that would have been unimaginable just years earlier. The magnetic field was mapped with extraordinary detail, revealing the structure of the magnetic forces surrounding the planet. The composition of Saturn's upper atmosphere was sampled directly through Cassini's mass spectrometer, collecting actual molecules from the planet's outermost layers. The rings were examined up close, revealing structure and composition that had remained hidden until these final moments. Scientists marveled at the wealth of data streaming down from the spacecraft as it conducted these daring maneuvers. Every measurement was precious, every data point valuable, because these would be the last measurements Cassini would ever make. And then, on September 15, 2017, it was over. Cassini's final dive was different from the others. This time, there was no pull-up maneuver to escape Saturn's gravity. This time, the spacecraft continued downward, crossing the planet's cloud tops and plunging into the atmosphere. The spacecraft's instruments continued recording data, streaming measurements back to Earth in real time. Scientists watched in real time as their spacecraft descended into the Saturnian atmosphere, its instruments functioning even as the extreme pressure and heat began to overwhelm the delicate electronics. Eventually, the signal faded and contact was lost. Cassini had completed its final mission. The spacecraft that had traveled billions of kilometers and spent 13 years in service had been returned to Saturn. Drawn into its gravitational embrace, its atoms dispersed into the atmosphere of that magnificent world. But the story didn't end there. The data Cassini had collected during its grand finale was extraordinary. And as scientists began to analyze the measurements, they made discoveries that left them astonished. The gravity data was particularly surprising. When Cassini measured Saturn's gravity field with such high precision, scientists were able to determine how the planet's mass was distributed internally. They were trying to solve an old mystery. How fast does Saturn actually rotate? This sounds like a simple question, but Saturn's atmosphere is dynamic and turbulent, with different layers rotating at different speeds. The solid interior of Saturn rotates at a different rate than the clouds we observe from Earth. Determining the true rotation rate requires understanding the internal structure. The gravity measurements revealed something unexpected. The data didn't match what the leading planetary models predicted. Specifically, the measurements of the even gravity harmonics, the coefficients labeled J6, J8, and J10, were larger than existing models suggested they should be. These higher-order gravity harmonics are sensitive to the internal structure of the planet, particularly to how rapidly the interior rotates and how the planet's mass is distributed at different depths. When scientists tried to match these gravity measurements with traditional models that assumed the planet rotated as a rigid body, the numbers simply didn't work. Something was fundamentally different about Saturn's interior structure than what the models had predicted. This discovery led to a revolutionary rethinking of Saturn's internal structure that sent shockwaves through the planetary science community. Scientists developed new models that suggested Saturn's interior doesn't rotate as a solid sphere, as the old models had assumed. Instead, the interior might rotate on cylinders, with different layers at different depths, rotating at different rates, a concept known as cylindrical differential rotation. This type of differential rotation had profound implications for how scientists understood planetary formation and evolution. It suggested that Saturn's interior was far more complex and dynamic than anyone had expected. The planet wasn't simply a sphere of hydrogen and helium with perhaps some heavier elements concentrated at the core. Instead, Saturn appeared to have a sophisticated internal structure with complex dynamics and layering that created the gravity anomalies Cassini had detected. The implications extended beyond Saturn, affecting how scientists thought about Jupiter and exoplanetary systems as well. If Saturn's interior was more complex than expected, perhaps other gas giants were too, suggesting that our models of planetary formation might need substantial revision. The implications were staggering. If Saturn's interior really did rotate on cylinders, with different rotation rates at different depths, this fundamentally changed our understanding of how Saturn formed and evolved. It suggested that Saturn might have a more massive core than previously believed. It indicated that the distribution of heavy elements throughout Saturn's interior was different from what planetary scientists had theorized. The discovery didn't just affect Saturn, it had implications for how we understand other gas giants. Jupiter has its own internal complexity, and similar processes might be occurring there. Understanding Saturn's interior structure provided insights into how gas giants throughout our solar system and beyond are actually put together. But the surprises didn't end there. Cassini's magnetometer, the instrument designed to measure Saturn's magnetic field, returned data that was equally perplexing. Scientists had expected Saturn's magnetic field to have certain characteristics based on what they knew about how planetary magnetic fields are generated. After all, they had studied planetary magnetism for decades. They had developed theories, conducted experiments, and built computational models. They thought they understood the basics of how these fields work. However, the measurements showed something completely unexpected. Saturn's magnetic field appeared to have no discernible tilt. This was shocking. Planetary magnetic fields are typically tilted relative to the planet's axis of rotation, sometimes dramatically so. Earth's magnetic field is tilted by about 11 degrees, and this tilt is well understood through the physics of how Earth's interior convection generates the field. Jupiter's magnetic field is tilted by about 10 degrees. Scientists had expected Saturn's magnetic field to show a similar tilt, perhaps 10 degrees, perhaps more. But the data suggested it didn't, or at least the tilt was far smaller than expected, smaller than could be easily explained by existing theories. This was mysterious because the mechanism that generates Saturn's magnetic field should produce a tilted field. Deep within Saturn's interior, liquid metallic hydrogen swirls and moves, and these movements of electrically conductive material generate the magnetic field through dynamo processes, the same fundamental mechanism that generates Earth's magnetic field. The pattern of motion should produce a field with a tilt, just as Earth's motion produces a tilted field. Yet here was Cassini showing that Saturn's magnetic field was nearly perfectly aligned with the planet's axis of rotation, aligned in a way that seemed to violate the principles scientists thought they understood so well. Scientists had to reconsider their understanding of the dynamo processes occurring inside Saturn. Perhaps the interior convection patterns were fundamentally different from what they'd thought, arranged in such a way that the tilting effects canceled out. Perhaps the distribution of metallic hydrogen in Saturn's interior was arranged in such a way as to cancel out any tilt that might otherwise develop. Perhaps there was some stabilizing mechanism operating at Saturn's core that prevented the magnetic field from tilting. Understanding why Saturn's magnetic field behaved so differently from Jupiter's and Earth's became a new puzzle for scientists to solve, a puzzle that would require rethinking fundamental planetary physics. Another major discovery came from Cassini's atmospheric sampling instruments, providing the most direct evidence yet of Saturn's upper atmospheric composition. As the spacecraft plunged through the grand finale orbits and eventually into Saturn's atmosphere itself, the ion and neutral mass spectrometer aboard Cassini directly sampled the composition of Saturn's outermost atmosphere. These measurements had never been made before with such precision. Scientists were able to determine the exact concentrations of various chemical species in Saturn's atmosphere, identifying specific molecular signatures that had remained unknown. They gathered direct measurements of gases, ions, and neutral particles that make up the world below the visible clouds. They detected hydrogen, helium, and trace amounts of heavier elements and compounds. This compositional data would help refine models of Saturn's atmospheric chemistry and dynamics, providing crucial inputs for improved computational models of how the planet's weather systems form and evolve. It would inform future missions that might send probes deeper into Saturn's atmosphere to study the planet's weather and weather patterns, probes that would build upon Cassini's final measurements to probe even deeper into Saturn's secrets. Similarly, Cassini's cosmic dust analyzer collected samples of material from Saturn's rings as the spacecraft flew through the gap between the planet and the rings during the grand finale dives. These nanometer-sized ring particles, collected directly by Cassini's instruments, provided the first-ever physical samples of ring material obtained in situ. Scientists could now analyze the composition of the rings in unprecedented detail using sophisticated laboratory techniques. They could determine what elements and compounds made up the ring particles, understanding more about the ring's origin and evolution. The analysis revealed that the rings contained water ice mixed with darker materials, possibly silicates or carbonaceous compounds. The rings revealed themselves to be even more complex than expected, with significant variations in composition and structure from one region to another. Some parts of the rings were predominantly water ice, while other regions contained higher concentrations of organic compounds, suggesting that different parts of the rings had different origins or had been processed by different mechanisms over time. The final images Cassini transmitted were breathtaking. 2 days before the mission-ending plunge, Cassini used its wide-angle camera to capture a grand farewell mosaic of Saturn and its rings. The spacecraft obtained 42 separate images in red, green, and blue, which scientists stitched together to create a full natural color view of Saturn and its ring system. The images captured not just Saturn itself, but several of its moons, Prometheus, Pandora, Janus, Epimetheus, Mimas, and Enceladus. Each moon visible in the final images had its own story, its own contributions to our understanding of the Saturnian system. These final images were remarkably similar to images Cassini had taken at the beginning of its mission. A comparison between an image from 2001 and one from 2017 showed how much both the spacecraft and its instruments had aged, yet how determined the mission had been to study this magnificent world. The parallel images created an emotional resonance, serving as bookends to one of the most successful planetary missions in human history. They reminded everyone involved that this was not merely a spacecraft, but the product of human dreams and determination. As the grand finale orbits continued, Cassini's cameras captured unprecedented close-up views of Saturn's atmosphere in breathtaking detail. The spacecraft obtained the highest resolution images ever taken of Saturn's polar cyclones, swirling vortices of wind and cloud that exist at the planet's poles. These cyclones are enormous, spanning thousands of kilometers across, with wind speeds that rival the most powerful hurricanes on Earth. The images revealed the intricate structure of these storms, the layers of clouds at different altitudes stacked in perfect detail, and the aurora that plays across Saturn's poles, just as auroras dance across Earth's, though Saturn's auroras are far more intense and beautiful. The Saturnian aurora is generated by solar wind particles interacting with Saturn's magnetosphere, creating light shows that dwarf anything we see on our own planet. Cassini also provided close-up views of Saturn's famous hexagon, a massive geometric storm that surrounds the North Pole, one of the most peculiar and mysterious features in our entire solar system. This hexagon has puzzled scientists for decades. It's a perfect six-sided structure that persists in Saturn's atmosphere, a shape that seems almost too perfect to be natural, yet natural it is. The mathematics behind how such a possible geometric shape can form and persist in a fluid atmosphere has fascinated physicists and mathematicians. The close-up views revealed the internal structure of this unusual storm, with clouds and wind patterns that created the distinctive hexagonal boundary. Scientists observed smaller storm systems, spiraling around inside the hexagon, and they noted that despite the violent winds and dynamic atmosphere, the hexagon's shape remained remarkably stable. Understanding how this geometric structure maintains itself has become a focus of research for atmospheric scientists studying not just Saturn, but other planets and even our own Earth. The combination of all this data, all these unexpected discoveries, has taken years for the scientific community to fully process and understand. The data sets are enormous, containing measurements from dozens of instruments collected over 13 years. Even now, years after the mission ended, scientists are still publishing papers, analyzing the Cassini data, making new discoveries, and developing new theories about Saturn. Graduate students are building their dissertations on Cassini data analysis. Researchers in universities around the world are working with Cassini's observations, extracting new insights from the massive archive. The mission's scientific output is truly staggering, a legacy that will continue producing results for decades. The grand finale was designed to be a dramatic ending to a magnificent mission. But instead of providing a final summary of Saturn's secrets, it opened up new mysteries, new questions that scientists will be investigating for years to come. The data revealed that our understanding of Saturn was incomplete, that our theoretical models needed refinement, and that this gas giant still holds surprises for those who study it carefully. One of the most profound realizations that emerged from Cassini's data is that our models of planetary interiors, our theoretical frameworks for understanding how gas giants are structured and how they evolve, were incomplete. We thought we understood Saturn well enough to build detailed models of its interior. We thought we could predict what Cassini's instruments would measure. We were wrong. Saturn proved to be more complex, more dynamic, and more surprising than our theories predicted. This is a humbling reminder. that even after centuries of astronomical observation and decades of space exploration, the universe still has the capacity to surprise us, to challenge our assumptions, and to force us to reconsider our fundamental understanding of how worlds are made. The story of Cassini is ultimately a story about human curiosity and determination. It's a story about the hundreds of scientists who designed the spacecraft, the thousands of engineers who built it, the mission controllers who navigated it across billions of kilometers, and the researchers who have dedicated their careers to analyzing the data it collected. It's a story about what we can learn when we commit ourselves to understanding the universe around us. Cassini showed us that Saturn is not just a beautiful world to observe from afar, but a complex, dynamic, and fascinating realm that continues to teach us new lessons about how planets form, how they evolve, and what conditions might exist for life to emerge in places we never before thought possible. As we look back on Cassini's mission, we recognize that it represents one of humanity's greatest achievements in space exploration. The data it collected has already influenced the design of future missions. The discoveries it made have inspired a new generation of scientists and engineers. The images it sent back have captured the imagination of people around the world, and the mysteries it revealed ensure that scientists will be studying Saturn for decades to come, working to understand the secrets that Cassini unveiled during those final, unexpected moments when the spacecraft revealed that we still have so much to learn about our solar system. The grand finale wasn't an ending to our study of Saturn. It was merely the beginning of a new chapter in our quest to understand this magnificent world and all the secrets it continues to hold.